How could an entire millennium of brilliant minds struggle with basic shapes? What if the numbers you thought you knew held impossible secrets? For over 1,000 years, from the 5th to the 15th century, the sharpest thinkers of the medieval world grappled with questions that seemed simple on the surface, but hid an astonishing depth of complexity. Number 10. The unsolvable equations. Diophantine. In the bustling centers of medieval learning, from the House of Wisdom in Baghdad to the universities of Oxford and Paris, mathematicians often found themselves staring at equations that seemed to mock their best efforts. These were not the simple "what is x" problems that appear in school books today. These were Diophantine equations, named after an ancient Greek mathematician, Diophantus of Alexandria, whose work had made its way into the Arabic world and then, through translation, into Latin Europe. The core challenge of these equations was not just to find a value for x, but to find values for xy, or sometimes z, that were whole numbers, integers. The world of fractions and decimals, though increasingly understood, was often set aside for the purity of integers, which felt more fundamental, more God-given to many scholars of the age. One classic example that puzzled thinkers was finding integer solutions for equations involving squares. For instance, consider the equation times squared plus y squared equals z squared. Today, we might instantly think of the most famous set of solutions, 3, 4, and 5, because 3 squared 9 plus 4 squared, 16 equals 25, which is 5 squared. But the challenge was not just to find one such set, but to understand how to find all such sets, or to prove whether a given equation had any integer solutions at all. Muhammad ibn Musa al-Khwarizmi, a towering figure in 9th century Baghdad, whose very name gave us the word algorithm, dealt extensively with quadratic equations in his foundational text, the compendious book on calculation by completion and balancing. While he offered systematic ways to solve many forms of quadratics, his focus was largely on positive solutions, often expressed geometrically, and the leap to finding integer pairs for more complex Diophantine forms was a different beast altogether. His methods, while revolutionary for their time, did not provide a general framework for the integer problem. Later, across the Islamic world, mathematicians like Abu Kamil, working in Egypt around the 10th century, continued to explore algebraic problems. He wrote a commentary on al-Khwarizmi's work and delved into equations with higher powers and systems of equations, sometimes looking for rational solutions. The strict demand for integers often presented a dead end, a wall of numbers that seemed to offer no pattern or general rule. The methods were often ad hoc, specific to the particular equation, rather than a sweeping approach that could be applied universally. In Latin Europe, the arrival of these Arabic texts in the 12th and 13th centuries, often translated by scholars like Adelard of Bath or Robert of Chester, ignited a new passion for algebra. Leonardo Fofami, the great Italian mathematician of the 13th century, known for introducing the Hindu-Arabic numeral system to Europe with his Liber Abaci, also dipped his toes into Diophantine problems. In his lesser-known but significant work, Liber Quadratorum, or the Book of Squares, Fadlake explored problems related to finding numbers whose squares met certain conditions. He was fascinated by numbers which, when squared and added to another square, produced a third square. He found elegant solutions for specific types of such problems, demonstrating a profound understanding of number properties. However, his work, while brilliant, did not create a universal method to determine integer solutions for any given polynomial equation. He found particular pathways through the numerical maze rather than a grand map of the entire labyrinth. Scholars of the medieval era, despite their incredible ingenuity, lacked the powerful algebraic tools and abstract number theory frameworks that would be developed centuries later. They worked often by trial and error, by specific numerical examples or by geometric interpretations which, while inshable, sometimes limited their ability to generalize. When confronted with an equation like times squared plus y squared equals 3, for example, they might spend countless hours trying to find integer pairs. Every possible combination of small integers would be tested. They might realize that no such integers existed, but proving that definitively for all integers was another matter entirely. The methods available to them were often not sufficient for such proofs of impossibility. The struggle was not merely mathematical, it was also philosophical. For many, mathematics was seen as a way to uncover the divine order of the universe. If an equation derived from what seemed like fundamental principles yielded no whole number solutions, it could be perplexing. Was it a flaw in their understanding? Or did some equations simply exist without neat integer answers? Quest for integer solutions carried a weight of purity and completeness, making the lack of a general method for Diophantine equations a persistent source of frustration. Consider the famous problem of finding a number that, when squared, could be both increased and decreased by the same integer to form new squares. Sibaya tackled this problem in Liber Quadratorum, exploring numbers that satisfied such conditions. He managed to find specific integer solutions, demonstrating a sophisticated understanding of the underlying arithmetic. But the overall landscape of Diophantine problems, where equations could involve multiple variables raised to various powers, and where the solution had to be an integer, remained largely uncharted territory. The problem was exacerbated by the lack of a fully developed symbolic algebra. While Al-Khwarizmi used what we call rhetorical algebra, describing equations in words, and later, scholars like Jordanus de Nemori in the 13th century moved towards a more syncopated algebra, using some abbreviations, the full power of modern algebraic notation was still far off. Without clear, concise ways to manipulate abstract symbols representing unknown quantities, the task of proving general statements about integer solutions became incredibly cumbersome, if not impossible. Each equation often had to be treated as a unique case, requiring its own special approach. So, while medieval mathematicians could solve many specific Diophantine equations, particularly those linked to Pythagorean triples or similar number patterns, the idea of a universal method to determine the existence of integer solutions for any arbitrary polynomial entry. They chipped away at the problem, finding fascinating specific results, but the grand overarching theory that would one day tame these numerical beasts was still centuries away, leaving generations of scholars to ponder the silent, stubborn resistance of numbers that refused to be neatly defined. They left behind a legacy of dedicated effort, a testament to their relentless pursuit of numerical truth, even when the answers seemed to hide in plain sight or vanish completely. Quest for these integer solutions remained a challenging frontier, a realm where even the most brilliant minds often found themselves at a standstill, forced to admit the limits of their current knowledge and the unyielding nature of certain numerical relationships. Number 9. The Pi Puzzle. Imagine a medieval scholar hunched over a parchment trying to calculate the circumference of a giant wheel or the area of a perfectly circular fountain. To do this, they needed a value for pi, the mysterious constant that links a circle's diameter to its circumference. But pi is an irrational number, an endless, non-repeating decimal. And for medieval mathematicians, this presented an enormous challenge. How could you work with a number that could never be precisely written down, that forever stretched beyond the limits of their numeral systems and computational tools? For centuries, mathematicians knew pi existed, but pinning it down with accuracy was like trying to catch mist. The ancient Greeks, especially Archimedes, had made significant progress. Archimedes' method, described in his treatise, Measurement of a Circle, involved inscribing and circumscribing regular polygons around a circle. By increasing the number of sides of these polygons, he could get closer and closer to the circle's actual circumference and area. Using a 96-sided polygon, Archimedes famously determined that pi was between 3 and 10/70, approximately 3.1408, and 3 and 1/7, approximately 3.1428. This was an incredible feat, for its time providing a very practical range for pi. This knowledge was transmitted to the medieval world first through Arabic translations of Greek texts and then into Latin Europe. Mathematicians in the Islamic world, building on Greek and Indian knowledge, made further strides. Al-Khwarizmi's works, while foundational for algebra, did not focus intensely on pi calculation, but subsequent scholars did. For example, al-Biruni, a Persian polymath of the 11th century, used methods similar to Archimedes, but with even more sides, reportedly calculating pi to several decimal places. He was also aware of methods that involved approximations, drawing from Indian traditions where pi was sometimes approximated as the square root of 10, or more accurately as 3.1416. Jamshid al-Kashi, a Persian mathematician and astronomer working in Samarkand in the early 15th century, achieved an astonishing level of precision for pi. In his work, the treatise on the circumference, he calculated pi to an astounding 16 decimal places, using a polygon with 3 multiplied by 2 to the power of 27 sides. This was a monumental computational achievement, requiring immense patience and meticulous calculation. He expressed this value in what we now recognize as decimal form, a system that was then slowly gaining traction, though not yet fully universal. His work demonstrated the peak of computational ability in the medieval Islamic world. In Latin Europe, the situation was somewhat different. While scholars like Fima brought Hindu-Arabic numerals and many computational techniques to Europe, the direct pursuit of pi to extreme precision was not as central a focus as in the Islamic world. European scholars were more concerned with practical applications and the theoretical understanding of geometry, often relying on Archimedes' approximations or simpler fractions like 22/7 for 3 and 1/7 for calculus. Robert Grosseteste, an English scholar of the 13th century, and others like him, focused on the philosophical implications of geometry and number rather than raw computational accuracy for pi. They accepted the Archimedean bounds as sufficiently precise for their cosmological and practical needs. Difficulty lay not in grasping the concept of pi, but in the sheer laborious process of calculating it to more and more decimal places. The methods available were iterative and required increasingly massive computations with large numbers, all done by hand. There were no calculating machines, no quick ways to multiply or divide multi-digit numbers. Every single step was a manual operation, prone to error. Furthermore, the very nature of an irrational number posed a conceptual challenge. While they understood that pi was not a simple fraction, the idea of a number that could never be fully expressed, that went on forever without repeating, was profoundly unsettling in a world that valued order and finite perception. How could something so fundamental to a perfect shape, like a circle, be so imperfectly expressible? This philosophical hurdle, combined with the computational one, meant that while they had good approximations, the quest for ultimate precision felt like chasing a mirage. Nicole Erasmi, a brilliant French scholar of the 14th century, explored the representation of numbers and quantities. While he did not focus on pi specifically, his work on representing numerical values geometrically, and his early ideas on infinite series hinted at methods that would one day revolutionize how pi could be approached. However, his work was nascent, a seed planted for future generations, not a fully formed method for medieval pi calculation. The available numeral systems also played a role. Roman numerals were incredibly cumbersome for multiplication and division. The slow adoption of the Hindu-Arabic numeral system, which was more efficient for computation due to its positional value and the inclusion of 0, gradually eased some of the burden. But even with these new numerals, performing calculations with numbers involving many decimal places was a Herculean task. To add more digits to pi, one had to perform operations on numbers with an ever-increasing number of digits, and each such operation multiplied the possibility of error and the time required. The concept of limits, crucial for the later development of calculus, that would provide new ways to approximate pi through infinite series, was also not yet fully formed. While Archimedes' method implicitly involved a limiting process, the formal, mathematical language and conceptual framework for handling infinitely small increments or infinite sums were not available to medieval scholars. Could only approximate pi by brute force, extending the polygons to an ever greater number of sides, which quickly became computationally unmanageable beyond a certain point for the average scholar. So medieval mathematicians struggled with pi, not because they lacked intelligence, but because they lacked the powerful computational tools, the universal adoption of efficient numeral systems, and the advanced theoretical frameworks like calculation. They had good approximations for most practical purposes, but the true infinite nature of pi remained a deep well of mystery, a number that stubbornly refused to be neatly confined by the limits of their parchment and pen. It was a constant reminder of the elusive precision of the universe, always just beyond their grasp, pushing the boundaries of what they could calculate and comprehend. Number 8. The elusive prime patterns. The world of numbers, for medieval scholars, was a realm of profound mystery and divine order. Among these numbers, the prime numbers held a special, almost sacred significance. A prime number is a whole number greater than one that has only two positive divisors, 1 and itself. Think of 2, 3, 5, 7, 11, and so on. They are the building blocks of all other integers, like elementary particles in the numerical universe. But understanding their distribution, predicting where the next one might appear, or finding a general rule for their sequence proved to be an incredibly frustrating and enduring challenge. The ancient Greeks, particularly Euclid, in his Elements, had already established fundamental truths about prime numbers. Euclid famously proved that there are infinitely many prime numbers, a beautiful and powerful result. He also provided a method for finding prime numbers known as the sieve of Eratosthenes, which involves systematically eliminating multiples of numbers. These foundational ideas were known in the medieval Islamic world and through translation slowly became known in Latin Europe. However, knowing that primes exist infinitely and having a method to find them up to a certain point is very different from understanding their pattern or distribution. As one lists them out, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. They appear to jump around erratically. There's no obvious formula that tells you the 10th prime, or the 100th prime, or the millionth prime. This irregularity was deeply puzzling to minds accustomed to seeking order and symmetry in the universe. In the Islamic world, mathematicians like al-Biruni were interested in number theory, though their focus was often on perfect numbers, amicable numbers, and general arithmetic. The direct study of prime distribution as a theoretical problem was not a central preoccupation, perhaps because the tools to approach it were simply not available. They understood primality and factorization, which were essential for practical applications like astronomy and commerce, but the abstract pattern of primes remained elusive. In Europe, Leonardo fought the eye, with his profound grasp of number properties, certainly encountered prime numbers. His work, Liber Abaci, introduced concepts that laid the groundwork for more advanced number theory, but he did not delve into the mysteries of prime distribution. He focused more on practical arithmetic sequences and specific number puzzles. Problem was that medieval mathematics lacked the tools of advanced number theory and abstract algebra that would later prove crucial for investigating prime numbers. They did not have the concept of modular arithmetic in its modern form, nor the sophisticated analytical methods that would allow mathematicians in later centuries to propose theorems like the prime number theorem, which describes the asymptotic distribution of primes. They worked with integers directly, often by testing specific cases or looking for simple arithmetic progressions. Consider the challenge of trying to find large prime numbers. The only method was trial division, checking if a number could be divided by any smaller prime. This quickly becomes an impossible task for very large numbers. Without efficient algorithm or powerful computational aids, finding even moderately large primes was a monumental undertaking. Proving that a very large number was prime would take weeks or months of manual calculation, if it was possible at all. Moreover, the search for formulas that generate primes was a persistent yet unfulfilled quest. Medieval scholars might have wondered if there was an expression, a polynomial for instance, that would always produce a prime number. They might have experimented with simple forms, only to find that such expressions eventually produced composite numbers. This search was a dead end, because no such simple formula exists that generates only primes for all inputs. The failure to find such a formula, despite diligent effort, contributed to the perception of primes as inherently unpredictable. The conceptual hurdle was significant. The idea that randomness or irregularity could be inherent in something as fundamental as numbers was often at odds with the prevailing philosophical and theological views that emphasized divine order and mathematical harmony. While some acknowledged that God's ways were inscrutable, the mathematical quest was often driven by a desire to reveal that order. The apparent capriciousness of prime numbers therefore stood as a nagging puzzle. Even when scholars investigated specific types of numbers related to primes like Mersenne to the power of n-1, they did so without a deep theoretical understanding of why some were prime and others were not. They could test them, but they could not predict. The distinction between discovering a prime and understanding the underlying structure that governs all primes was a vast chasm. Nicole Orsme, who made strides in understanding infinite series and graphing qualities, did not directly address prime patterns, but his innovative thinking about infinite processes hinted at a new way of looking at numbers, one that was not fully developed until later centuries. However, his contributions were more towards the foundation of what would become calculus rather than number theory. The slow, painstaking process of manually checking for divisibility, the lack of abstract algebraic notation to generalize properties, and the absence of advanced analytical methods meant that prime numbers remained a tantalizing mystery. They were like scattered jewels on a vast, dark plain, visible when illuminated by direct examination, but with no clear path or map to predict where the next one might lie. Patterns that later mathematicians would uncover, subtle and profound, were simply beyond the reach of the tools and conceptual frameworks available to medieval scholars, leaving the prime numbers as a persistent enigma, stubbornly refusing to yield their secrets to human reason. The elusive nature of their distribution continued to baffle, leaving mathematicians with a deep appreciation for their fundamental importance, but an enduring frustration at their unpredictable nature. Number 7. The infinite paradoxes. Concept of infinity for medieval scholars was a source of both profound wonder and immense intellectual discomfort. How could something be endlessly large without end? What did it mean for a process to continue forever? These questions, passed down from ancient Greek philosophy, particularly Zeno's paradoxes, continued to torment thinkers through the medieval period. They struggled to reconcile the mathematical implications of infinity with theological and philosophical doctrines. One of the most famous paradoxes, Zeno's decapity paradox, stated that to reach any destination, one must first cover half the distance, then half of the remaining distance, then half of that remaining distance, and so on infinitely. This implied that motion was impossible because an infinite number of steps would have to be completed in a finite time. For a medieval scholar, this was not just a clever trick of logic. It touched upon the very nature of motion, time, and space, all crucial aspects of their understanding of the world. Another related paradox was Achilles and the tortoise. Achilles, a swift runner, gives a slow tortoise a head start. By the time Achilles reaches the tortoise's starting point, the tortoise has moved a little further. By the time Achilles reaches that new point, the tortoise has moved again, and so on. Zeno argued Achilles would never catch the tortoise. For medieval minds, this was deeply counterintuitive yet hard to disprove purely with the mathematics they possessed. Scholars in the Islamic world, like al-Kindi and Ibn al-Haytham, studied Greek philosophy and geometry engaging with Zeno's arguments. Ibn al-Haytham, in particular, made significant contributions to optics and geometry, and implicitly dealt with infinitesimally small quantities in his work on volumes foreshadowing calculus. However, a full, rigorous mathematical framework for dealing with actual infinity or infinite sums was not yet established. Their solutions often involved conceptual distinctions, for instance, distinguishing between potential infinity, something that can be endlessly extended, and actual infinity, a completed endless quantity, or by appealing to physical reality over abstract mathematical impossibility. In Latin Europe, the debates over infinity became intertwined with theological doctrines. God was considered infinite, perfect, and complete. Could there be other actual infinities? Could an infinite number of things exist? Prevailing view, heavily influenced by Aristotle, was that actual infinities were impossible in the physical world. Only potential infinity was allowed. The idea that a process could always be extended but never actually completed. This meant that while numbers could go on forever, there was no completed set of all numbers. Thomas Bradwardine, an English Merton College scholar in the 14th century, explored ideas related to motion and velocity, often touching upon the continuum and infinite divisibility. His work on ratios and proportions, while not directly addressing Zeno's paradoxes, grappled with the mathematical representation of continuous quantities, a challenge that inherently brings up questions of infinite subdivisions. However, he operated within the Aristotelian framework that denied actual infinites in the physical realm. Nicole Oresme, another 14th century giant perhaps, came closest to grappling with infinite series in a mathematically productive way. In his treatise on the uniform and difform, Oresme introduced graphical representations of changing qualities, which could be seen as precursors to coordinate geometry. More significantly, he analyzed sums of infinite series. He famously proved that the harmonic series 1 plus 1/2 plus 1/3 plus 1/4 and so on diverges, meaning its sum goes to infinity. He also demonstrated that other infinite series, like the sum of fractions where the numerator is 1 and the denominator is powers of 2, 1/2 plus 1/4 plus 1/8, and so on, could converge to a finite sum, in this case, 1. Oresme's work was revolutionary, but it still operated within conceptual constraints. While he understood that an infinite sum could have a finite value, his reasoning was often geometric or heuristic, rather than using the rigorous formalisms of modern calculus. He did not possess the concept of limits in the modern sense, nor the general theory of convergence and divergence that would later be developed. His insights were brilliant, but they were isolated breakthroughs in a landscape still dominated by philosophical caution regarding actual infinity. The problem for medieval scholars was multi-layered. Firstly, the lack of a proper mathematical language for infinity. They used words and sometimes diagrams, but no symbols for infinity or for the concept of limits. This made formal proofs difficult. Secondly, The philosophical and theological resistance to actual infinity constrained their mathematical explorations. If the existence of actual infinities contradicted divine perfection or logical consistency, then finding them in mathematics was seen as problematic. Paradoxes of Zeno, therefore, remained largely unresolved in a purely mathematical sense. Scholars like Jean Buridan, a contemporary of Orsmy, discussed them from a philosophical standpoint, attempting to resolve them by appealing to the physical nature of continuous motion, rather than by demonstrating a mathematical resolution for the infinite sums involved. They argued that motion was continuous and did not consist of discrete steps, thus avoiding the accumulation of infinite steps. The struggle with infinity highlighted the limitations of medieval mathematics, its dependence on geometry for rigor, its underdeveloped symbolic algebra, and its deep entanglement with philosophical and theological systems that often prioritized conceptual consistency over mathematical abstraction for its own sake. The infinite remained the frontier, a concept too vast and too profound to be fully contained by the mathematical tools of the era, leaving a lasting legacy of paradoxes that tantalized and perplexed the sharpest minds. They probed at its edges, sometimes making remarkable discoveries like Orsmy's work on series. But the vast, boundless ocean of infinity remained largely unmapped, its deepest secrets guarded from their grasp, forcing them to acknowledge the limits of human comprehension in the face of the truly boundless. Number 6. The never-ending numbers. Irrationality. Imagine trying to build something perfectly square, like a table or a window. You carefully measure each side to be exactly 1 unit long. Now, what about the diagonal across that square? Ancient Greek mathematicians discovered something truly unsettling about this diagonal. Its length could not be expressed as a simple fraction, a ratio of 2 whole numbers. This discovery of irrational numbers, like the square root of 2, was so profound and disturbing that it caused a fundamental crisis in the neat, orderly world of numbers known to them. This crisis, though intellectually tamed in later eras, continued to pose conceptual challenges throughout the medieval period. The Greeks, especially the Pythagoreans, believed that all quantities could be expressed as ratios of integers. When they found that the diagonal of a unit square, which by the Pythagorean theorem is the square root of 2, could not, it was a shock to their foundational beliefs. Such numbers were called incommensurable, meaning they had no common measure with other integers. They were not rational. This concept was transmitted to the Islamic world through translations of Euclid's Elements. Islamic mathematicians like al-Khwarizmi dealt with specific square roots in their algebraic calculations, often in the context of solving quadratic equations or geometric problems. They developed methods for approximating these values, for instance, by numerical techniques or by using continued fractions, which provided increasingly accurate rational approximations for irrationals. However, the fundamental nature of these numbers, that they could never be perfectly represented as a fraction, remained a conceptual hurdle. While they used these numbers in calculations and understood their geometric reality, their exact representation remained a challenge. For example, if you were solving a problem and the answer involved the square root of 5, you could not write it down precisely. You had to either leave it as a symbol or approximate it, which was always seen as a practical concession rather than an exact solution. This was particularly problematic in fields like astronomy, where high precision was desired. In Latin Europe, the full implications of irrationality continued to be debated. Faibu, in his Liber Abaci, certainly used numbers like the square root of 2 in his problem solving, but he would often approximate them or leave them in radical form. His focus was more on practical arithmetic and introducing the Hindu-Arabic numeral system, which was better suited for approximating these values with decimals than Roman numerals were. But the underlying issue of their exact representation persisted. the philosophical implication was significant. How could quantities exist that defied the neat, orderly world of integers and ratios? For many scholars, who saw mathematics as a reflection of divine order, the existence of numbers that could not be fully captured by ratios was unsettling. They were real geometrically, representing lengths or areas, but unreal numerically, in a perfect rational sense. Concept of a continuum, a line that is infinitely divisible and contains points that correspond to both rational and irrational numbers, was not fully developed or formally understood in the way it would be with modern real numbers. While Aristotle's ideas about the continuum are influential, the mathematical tools to rigorously define and manipulate all points on that continuum, including the irrationals, were simply not there. Without a clear understanding of the real number line and the methods for constructing these numbers, they remained elusive. Scholars often resorted to classifying these numbers geometrically. A length that could be constructed with a compass and straightedge was considered constructible, even if its numerical value was irrational. But a number that was numerically irrational and also not constructible by these specific tools, like the cube root of 2, related to the duplication of the cube problem, or pi, related to squaring the circle, was even more challenging. The methods of classical geometry, while powerful, did not provide a way to exactly represent all numerical quantities. The lack of a general theory of numbers, and particularly the absence of concepts from modern analysis and set theory, meant that medieval mathematicians could not fully grasp the density of irrational numbers, or how to rigorously define them through limits or cuts. They knew these numbers existed and could work with them approximately, but their exact nature and place in the broader numerical universe remained a profound source of bewilderment. Robert Grosseteste and other scholars at places like Merton College in Oxford, while deeply interested in the mathematical underpinnings of natural philosophy and physics, did not solve the fundamental conundrum of irrational numbers. Their work on ratios and proportions, while sophisticated, did not provide a way to perfectly incorporate all incommensurable magnitudes into a unified numerical system that was simultaneously comprehensible and precise. So, while medieval mathematicians learned to live with irrational numbers, to approximate them for practical purposes, and to manipulate them algebraically in their radical forms, they did not fully resolve the deep conceptual challenge they posed. The idea of a number that never truly ended, that could not be written as a neat fraction, that broke the beautiful simplicity of integer ratios, remained a powerful reminder of the limitations of their numerical systems and their quest for absolute precision and perfect order in the universe of mathematics. They dealt with them, but they did not fully tame them. The never-ending numbers remained a permanent, yet perplexing, fixture on the mathematical landscape. Number 5. The zero that wasn't nothing, and numbers less than 0. Imagine a time when the number 0 was a revolutionary concept, and negative numbers were often viewed with suspicion or ignored entirely. For medieval mathematicians, particularly in Europe, embracing these concepts which are so fundamental to our mathematics today was a long and often contentious journey. The zero that wasn't nothing and the idea of numbers less than 0 presented profound conceptual and practical difficulties. The concept of 0 has a complex history. It originated in ancient India as a placeholder in positional numeral systems, allowing for numbers like 10, 100, and 1000 to be written unambiguously. It also functioned as a number in its own right, signifying nothing or empty. This Indian system, complete with 0, was adopted and refined in the Islamic world. Al-Khwarizmi's compendious book on calculation by completion and balancing used these Hindu Arabic numerals and 0 extensively. 0 was crucial for his algebraic methods. For instance, when an equation was reduced to a form like x equals nothing, he used it to represent an empty position or the result of a subtraction when the numbers were equal. However, when these numerals and ideas made their way to Europe through translations in the 12th and 13th centuries, they faced resistance. Concept of zero as a number, nihil or cipher from the Arabic surf, was difficult for many to grasp. How could nothing be a number? Aristotle's philosophy, which dominated European thought, emphasized tangible quantities and often struggled with the abstract notion of absence as a mathematical entity. Practical considerations also played a role. Merchants and accountants sometimes found the concept confusing and prone to error or even fraud, fearing that a zero could be easily added or removed to alter sums. Leonardo Fautiae, in his Liber Abaci of 1202, was a major proponent of the Hindu-Arabic numerals, including zero. He showed how computations, especially multiplication and division, became dramatically simpler with these new digits compared to cumbersome Roman numerals. He demonstrated zero's function as a placeholder and as the result of a subtraction, helping to popularize its use. Yet, even with Fifamig's advocacy, the full acceptance of zero as a number, with all its properties, took time. It was seen as a tool, a symbol, but its status as a full-fledged number, equal in standing to 1 or 2, was debated for centuries. Even more challenging were negative numbers. In ancient India, Brahmagupta, in the 7th century, already had rules for operations with positive and negative numbers, which he called fortunes and debts. These ideas also passed into the Islamic world. Abu Kamil and al-Karaji, among others, sometimes encountered negative numbers as solutions to equations, though they often rejected them as absurd or impossible in practical contexts, as they could not represent a physical quantity like a length or a number of apples. Omar Khayyam, when solving cubic equations geometrically, would only consider positive roots, ignoring negative ones. In Latin Europe, negative numbers were even more problematic. They could not be readily understood as counts of anything. How could you have -3 cows? While they could be seen as debts in financial contexts, their abstract mathematical interpretation was deeply unsettling. Mathematicians would often phrase problems and solutions in ways that avoided negative results. If an equation yielded a negative answer, it was typically rejected as meaningless or indicating that the problem had no true solution. Fib-Aul, in his work, sometimes encountered negative numbers, for example, when solving systems of linear equations. He might describe a negative answer as a debt or acknowledge it as a valid solution in a specific financial context. But he often stated that such problems had no useful or correct solution in the physical sense. For instance, he might say that if a problem resulted in a negative value for a quantity of goods, it meant the problem was ill-posed or had no practical answer. Journanus de Nemours, a Parisian mathematician of the 13th century, while advancing algebraic notation, still largely restricted his focus to positive quantities and numbers. His problems and solutions were always framed in terms of true numbers, meaning positive ones. Concept of a number line extending infinitely in both positive and negative directions was simply not part of the common mathematical understanding. Numbers were seen as existing from 1 onwards, with 0 as a boundary or a placeholder. The main reasons for this struggle were philosophical and practical. Philosophically, a number was usually associated with a measurable quantity, and negative quantities were difficult to visualize. Practically, while negative numbers could represent debts, performing operations like multiplying 2 negative numbers to get a positive one felt counterintuitive and lacked an obvious real-world analogy that was easily grasped. So, for medieval mathematicians, 0 was a vital tool that slowly gained acceptance, though its status as a full number was long debated. Negative numbers, while appearing in intermediate steps of calculations or as debts, were generally treated as fictitious or absurd solutions, largely excluded from the realm of true or proper numbers. The journey towards a unified number system that fully embraced zero and negative numbers was a gradual one, stretching beyond the medieval period, leaving many scholars perplexed by the numerical entities that challenged their intuitive understanding of what a number could be. They grappled with these concepts, recognizing their utility in specific contexts, but often stopping short of a full theoretical embrace, thus leaving the numerical landscape partially charted with unexplored territories to the left of zero. Number 4. The mystery of the missing dimensions. Cubic equation. The world of algebra in the medieval period was a vibrant and growing field, building upon the foundations laid by earlier civilizations. While quadratic equations, those involving an unknown squared, could often be solved systematically, equations involving an unknown cubed, known as cubic equations, presented a much deeper and more frustrating puzzle. For centuries, the general solution to cubic equations remained elusive, a missing dimension in their algebraic tuquequate, stumping even the most brilliant minds. The ancient Greeks had approached some cubic problems geometrically, often intersecting conic sections like parabolas and hyperbolas to find solutions. This method was powerful for specific cases, but did not provide a general algebraic formula that could be applied universally, much like the quadratic formula applies to all quadratic equations. This geometric approach was carried forward into the Islamic world. Muhammad ibn Musa al-Khwarizmi's groundbreaking work introduced systematic algebraic methods, but his focus was primarily on linear and quadratic equations. He presented various types of quadratic equations and their solutions, often with geometrical justifications. However, he did not tackle cubic equations in a systematic way. The true hero of the medieval cubic equation saga is Omar Khayyam, the Persian polymath of the 11th and 12th centuries, perhaps more famous for his poetry, but a brilliant mathematician and astronomer. In his treatise on demonstrations of problems of algebra and al-Muqabala, Khayyam classified various types of cubic equations, recognizing that some could have positive roots, some negative, and some might have multiple roots. But like his predecessors, he rejected negative roots as impossible for practical problems, focusing only on positive solutions. Khayyam's genius lay in his systematic use of conic sections to solve cubic equations. He showed how to solve 14 different forms of cubic equations by finding the intersection points of parabolas and hyperbolas. For example, to solve a cubic equation like times cubed plus a squared times equals b cubed, he would convert it into finding the intersection of two conics. This was an astonishing achievement. Demonstrating a profound understanding of geometry and its connection to algebra, however, there were significant limitations. Khayyam's solutions were geometric. They provided a way to construct the solution as a length, but they did not provide a general algebraic formula involving only the coefficients and basic arithmetic operations: addition, subtraction, multiplication, division, and root extraction. For every new form of cubic equation, a new geometric construction might be needed, or a new combination of conics. This meant that while he could find the value of x, he couldn't write it down as a single, neat algebraic expression. The reliance on geometric constructions meant that the precision of the solution was dependent on the accuracy of the drawing. Furthermore, some cubic equations have three distinct real solutions. Some have one, and some have one real and two complex solutions. Khayyam's geometric methods were excellent for finding positive real solutions, but could not easily reveal multiple roots or the nature of other types of solutions, which would be explored centuries later with the development of complex numbers. The concept of numbers that involved the square root of negative numbers was entirely alien to medieval thought, leaving these missing dimensions of the cubic problem unsolved. In Latin Europe, the works of al-Khwarizmi arrived and were translated, laying the groundwork for algebraic development. Fibha, in his Liber Abaci, primarily focused on linear and quadratic equations and practical arithmetic, not delving into the complexities of cubic equations. While some isolated attempts were made, the full systematic geometric approach of Khayyam was not widely adopted or understood in Europe until much later. European scholars primarily lacked the sophisticated understanding of conic sections required for Khayyam's methods. The conceptual hurdle was immense. Medieval algebra, even in its most advanced forms, was largely rhetorical or syncopated, meaning equations were described in words or with limited abbreviations. A truly symbolic algebra where variables and operations were represented abstractly was yet to come. Without this symbolic framework, deriving and expressing a general algebraic formula for the cubic equation was virtually impossible. Each problem had to be approached almost as a unique geometric puzzle. Jarnanus de Nemours, a leading Parisian mathematician of the 13th century, made significant strides in algebraic notation and solving equations. He developed systematic methods for solving linear and quadratic equations, sometimes using general letters for quantities, pushing algebra closer to a symbolic form. However, his work did not extend to a general solution for cubic equations, remaining within the realm of solvable quadratics and their applications. So while Omar Khayyam made incredible breakthroughs in solving cubic equations geometrically, the medieval period, both in the Islamic world and in Latin Europe, did not produce a general algebraic formula for them. The missing dimension of these equations remained elusive, a profound puzzle that required a leap in both algebraic notation and the conceptual understanding of numbers beyond physical quantities. The search for a neat, universally applicable solution like the quadratic formula would continue to tantalize mathematicians for centuries after the medieval era, a testament to the stubborn resistance of numbers raised to the third power. The struggle for a general algebraic method for cubics represents a pinnacle of unsolved medieval algebraic problems, a frontier that remained just out of reach despite extraordinary individual brilliance. Number 3. The angle that refused to divide. Imagine a medieval artisan tasked with perfectly dividing a specific angle, say for a stained glass window or a navigational instrument, into 3 equal parts, using only the most basic tools: a compass to draw circles and measure lengths, and an unmarked straightedge to draw straight lines. Sounds simple, right? Yet, this seemingly straightforward geometric challenge, known as the trisection of an angle, utterly stumped scholars throughout the medieval period and for centuries thereafter. It was one of the 3 great impossibility problems of ancient Greek geometry, and its unsolvability under the given rules continued to baffle and frustrate the sharpest minds. The problem itself is elegant in its simplicity. Given any arbitrary angle, construct an angle that is exactly 1/3 the size of the original. The rules were strict, inherited from Euclid. Only a compass and an unmarked straightedge were permitted. No measuring devices, no protractors. No folding paper, no sliding rules. The ancient Greeks had already explored this problem extensively. While they found ways to trisect specific angles, like a right angle, which is 90 degrees, could be trisected into 3 30-degree angles using basic constructions, and developed methods that used tools beyond the compass and straightedge, like the noesis construction involving a sliding rule, or specific curves like the Archimedean spiral or the conchoid of Nicomedes. They could not find a universal method applicable any angle using only the elodie. This fundamental limitation was passed down through history. In the Islamic world, where Greek geometry was preserved and advanced, mathematicians inherited this challenge. They were aware of the ancient attempts and continued to explore methods. For instance, Abu Sahl al-Qi, a 10th century Persian mathematician, devised a mechanical method involving a compass and a graduated ruler for angle trisection. However, this method explicitly violated the unmarked straightedge rule, which meant it was a practical solution, but not a proof of constructibility under Euclidean constraints. Others, like al-Biruni, also discussed methods involving specific curves, While these solutions were ingenious and perfectly valid mathematically, they bypassed the core problem of strict Euclidean constructibility. The allure of solving it with only compass and straightedge was immense. It was a test of pure geometric elegance, a challenge that seemed so basic yet proved utterly resistant. Scholars spent countless hours trying different combinations of circles and lines, hoping to stumble upon the elusive construction. Each failure only deepened the mystery and the resolve to find a solution. When Greek geometric works, particularly Euclid's Elements, were translated into Latin in Europe, first from Arabic in the 12th century and then directly from Greek in the 13th, the problem of angle trisection became a significant focus for European geometers. Scholars like Adelard of Bath, one of the earliest translators of Euclid, and later figures like Robert Grosseteste and Roger Bacon, certainly would have been aware of these classical impossibility problems. They meticulously studied Euclid, but Euclid himself did not provide a compass and straightedge solution for general angle trisection. The problem persisted because the underlying mathematical reason for its impossibility was beyond the scope of medieval algebra and number theory. It was not until the 19th century that this problem was definitively proven impossible. Using only a compass and straightedge, a proof that required advanced algebraic field theory, specifically demonstrating that trisection of an arbitrary angle leads to the construction of a number that is a root of an irreducible cubic polynomial whose degree is not a power of 2. Medieval mathematicians simply did not have the conceptual tools to understand or prove this. They did not have the idea that geometric constructions could be translated into algebraic equations of specific degrees, and therefore deduce impossibility based on the nature of these algebraic equations. Their struggles manifested in various ways. Some would propose what seemed like valid constructions, only for their peers to meticulously dissect them and find flaws. These flaws were often subtle. A slight approximation, a dependence on an unstated assumption, or the implicit use of a tool more powerful than an unmarked straightedge. The very act of trying and failing, refining their understanding of what was possible with basic tools, defined their engagement with this problem. For scholars like Nicole Oresme, who were pushing the boundaries of mathematical thought with their work on quantities and rates of change, the angle trisection problem still represented a classic, unresolved geometric puzzle. While Oresme himself focused on different areas, the legacy of these impossibility problems cast a long shadow, reminding mathematicians that not all geometric questions could be answered by the available instruments. The trisection of an angle was more than just a geometric curiosity. It was a symbol of the limits of classical geometry. It highlighted the profound difference between what could be drawn approximately and what could be constructed exactly with the prescribed tools. Persistent failure to find a solution, despite centuries of effort by brilliant minds, was a testament to the deep hidden mathematical principles that governed what was geometrically possible, principles that remained shrouded in mystery throughout the medieval age, leaving the elusive angle forever resisting exact division by simple means. Number 2. The impossible cube challenge. Imagine a medieval scholar, perhaps an architect or a craftsman, pondering how to double the volume of a cubic altar or a storage chest. They might naturally think, if I double the side length, the volume will double. But that's not how cubes work. If you double the side length, you get 8 times the volume. The real challenge, known as the duplication of the cube, or the Delian problem, was to construct a new cube with exactly twice the volume of an original cube. This seemingly simple task, using only a compass and an unmarked straightedge, proved to be one of the great geometric impossibilities that frustrated and perplexed mathematicians throughout the medieval era. The problem originated in ancient Greece, reportedly, from an oracle at Delos who demanded a new altar with double the volume of the existing one to stop a plague. The Greeks quickly discovered that this was no easy feat. If the original cube has a side length of a, its volume is a cubed. To double the volume, the new cube would need a side length of x, such that x cubed equals 2 cubed. This means x must be equal to a multiplied by the cube root of 2. Problem then boils down to constructing a length equal to the cube root of 2, given a unit length. Like the trisection of an angle, the rules for this construction were strict: only a compass for drawing circles and measuring lengths, and an unmarked straightedge for drawing straight lines. No other tools, no sliding rules, no measuring scales. The ancient Greeks had recognized the difficulty and explored methods involving other curves or mechanical devices. Menanachmus, a student of Plato, showed that the problem could be solved by finding the intersection of two parabolas, or a parabola and a hyperbola. Archimedes also offered a solution involving elusive construction, a sliding rule. These ingenious solutions existed, but they always violated the strict compass and straightedge rule. This classical problem found its way into the medieval Islamic world through translations of Greek geometric texts. Mathematicians like Alcuin and Omar Khayyam engaged with it. Omar Khayyam, the brilliant Persian mathematician, famously used the intersection of conic sections to solve cubic equations. The duplication of the cube being equivalent to solving the cubic equation times cubed equals 2 fit perfectly into his geometric framework. Using parabolas and hyperbolas, he could construct the length of the side of the doubled cube by finding the intersection point of these curves. However, while Khayyam's method provided a geometrically precise solution, it was not a compass and straightedge construction. It required the ability to draw conic sections, which cannot generally be done with only these two tools. Therefore, for the medieval Islamic scholars who understood Khayyam's work, the problem was solved in a geometric sense, but the original challenge under the strict Euclidean constraints remained. They understood that the solution lay beyond elementary constructions. In Latin Europe, the arrival of Greek and Arabic geometric texts, particularly Euclid's Elements, fueled a renewed interest in classical problems. Scholars like Adelard of Bath in the 12th century or later, Robert Grosseteste in the 13th, absorbed these geometrical challenges. They painstakingly studied the limits of what could be done with compass and straightedge, but the duplication of the cube remained stubbornly out of reach. The reason for its impossibility, much like angle trisection, lies in advanced algebraic theory that was centuries beyond medieval understanding. It was not until the 19th century that it was rigorously proven impossible, using only a compass and straightedge. Proof involved showing that constructing the cube root of 2 requires solving a cubic equation whose roots cannot be expressed using only square roots, which is the limit of what compass and straightedge constructions can achieve. Medieval mathematicians had no concept of field extensions or Galois theory to make such a proof. Their attempts would have involved endless permutations of lines and circles, drawing, measuring, and checking, always coming up short of the exact ratio. They would have come to the conclusion that it was extraordinarily difficult, perhaps impossible with those tools, but they lacked the theoretical apparatus to definitively prove that impossibility. The philosophical implications were significant. If geometry was a reflection of divine order, why would such a seemingly simple problem be unsolvable? It challenged their understanding of what could be known or constructed in the mathematical universe. The problem, therefore, stood as a monumental obstacle. Despite brilliant geometric solutions from the Islamic world, the rigorous constraint of compass and straightedge meant that the duplication of the cube remained an impossible feat for medieval European scholars, a constant reminder of the profound limitations of even the most Bedums, the deprode limitations of even the most Bedus, the profound limitations of even the most Bedrums that dipped into higher algebrations of ease. It was a problem that forced them to confront the limits of their construction methods, a silent testament to the hidden complexities of simple-looking shapes and volumes. The quest for the impossible cube continued to tantalize and frustrate, leaving an enduring mark on the landscape of unsolved mathematical challenges. Number 1. The quest for a perfect circle square. Imagine a medieval scholar, perhaps a skilled mason or a philosopher mathematician, grappling with a task that sounds almost mystical, constructing a perfect square that has exactly the same area as a given circle. This seemingly straightforward geometric challenge, known as squaring the circle or quadrature of the circle, was the most famous and persistent of the three great geometric impossibility problems inherited from antiquity. For over 1,000 years, it captivated, tantalized, and ultimately stumped the brightest minds across the medieval world, proving to be an insurmountable barrier with the tools available to them. The problem is deceptively simple to state. Given a circle, construct a square that has precisely the same area, using only a compass and an unmarked straightedge. If a circle has radius, its area is pi multiplied by r squared. If a square has side length, its area is s squared. So, to square the circle, one needs to construct a side, such that squared equals pi multiplied by r squared, or s equals r multiplied by the square root of pi. This boils down to constructing the length of the square root of pi using only a compass and straightedge. The ancient Greeks had already spent centuries on this. Hippocrates of Chios made early progress, showing how to square certain curved figures called lunes, but not the circle itself. Later, Archimedes provided a brilliant method for approximating the area of a circle by inscribing and circumscribing polygons, giving a good approximation for pi but not an exact construction for squaring the circle. The fundamental difficulty lay in the elusive nature of pi, which they knew was a number that could not be expressed as a simple fraction. This profound problem entered the medieval mathematical tradition through translations of Greek works, particularly Euclid's Elements and Archimedes' writings, into Arabic and then into Latin. Islamic mathematicians, while excelling in algebra and trigonometry, also continued the geometric pursuits. They explored methods similar to Archimedes for approximating pi, achieving remarkable precision as seen with Jamshid al-Kashi's calculations. However, the exact squaring of the circle with compass and straightedge remained unsolved. They knew it was difficult, and some, like al-Biruni, probably suspected it was impossible. But they lacked the mathematical framework to prove it. The challenge for them was twofold. Firstly, the computational difficulty of pi. While they had good approximations like 22/7, 3.1428, or more precise ones like 355 divided by 113, 3.141559, none of these were the exact value. Squaring the circle required the exact value of pi, not just an approximation. Secondly, and more profoundly, was the constraint of using only a compass and straightedge. These tools limit constructions to lengths that are solutions to quadratic equations or sequences of such equations, essentially only allowing constructions involving square roots. In Latin Europe, with the influx of Greek and Arabic texts from the 12th century onwards, scholars became intensely focused on geometry. Figures like Leonardo Fobayi, while celebrated for introducing Hindu-Arabic numerals, also worked on geometrical problems. He recognized the classical problems, but did not offer a compass and straightedge solution for squaring the circle. His emphasis, like many of his contemporaries, was more on practical geometry and arithmetic. Problem became a touchstone for mathematical ability and a source of great intellectual frustration. Scholars would publish proposed solutions only for their peers to meticulously examine them and find subtle flaws. These flaws often involved implicitly using a tool more powerful than the allowed compass and straightedge, or making an unstated assumption, or simply providing an approximation rather than an exact solution. Quest often led to dead ends, reinforcing the persistent mystery. The fundamental reason for its impossibility, which medieval scholars could not have known, is that pi is a transcendental number. This means it is not the root of any non-zero polynomial with integer coefficients. A number that can be constructed with a compass and straightedge must be an algebraic number, specifically one that can be derived through a finite sequence of square root extractions. Since pi is transcendental, it cannot be constructed in this way, and therefore the square root of pi also cannot be constructed. This proof, provided by Ferdinand von Lindemann in 1882, relied on advanced concepts of algebra and number theory that were centuries beyond the medieval era. For medieval scholars, the inability to square the circle meant either that pi was an ungraspable, infinitely complex number, or that their methods were simply insufficient. The theological implications were also significant. If God created a perfect circle, why could it not be perfectly squared by human reason using elementary tools? This question often bordered on the philosophical and religious. Despite the continuous effort, including ingenious approximations and a deep understanding of geometry, the quest for a perfect circle square remained unfulfilled throughout the medieval period. It stood as a formidable, enduring symbol of the limits of human knowledge and the stubborn resistance of certain mathematical truths to the tools available at the time. The circle and the square, two fundamental geometric shapes, stubbornly refused to yield their secret of exact equivalence under the prescribed rules, leaving a legacy of intellectual struggle that stretched across 1,000 years. A testament to the perplexing nature of what seems simple but is profoundly complex.